I'm on a quest to build a fully automatic turntable, but this is one that I want to play my good records on. In the last video of this series, we went over my initial design for this turntable, which is just something that plays 7-inch records. Nothing too complicated, just one size. And I basically had this turntable working perfectly. It would gently place the stylus at the beginning of the record, and then at the end of the record it would pick itself up and return itself home. That's not to say it didn't have problems though, and it wasn't 100% accurate. It would get there about maybe 99% of the time, but I still wanted to close that 1% gap. The turntable speed was questionable, mostly because all the parts were 3D printed, and it would gradually increase in speed over time. One of those problems would be solved by finalizing all the parts, and the other one I'd worry about later. It worked well enough as is, anyway. With those successes, my ambitions grew beyond what I originally planned for, and this introduced a ton of scope creep. So today we're going to take a look at some of those revisions and what went wrong along the way, and what didn't work, what did work, and what we plan to do in the future a little bit. And we'll see how we ended up here. Now I'm not going to go into super specifics on every single part of the turntable, that would just take way too much time, and I want to do more building than talking anyway. So we'll just go over the things that I find to be most important. So let's just get to it. The first part of finalizing the design that I chose to go with was making the surface for everything to mount to. So I went with wood to do this, since that was all I was capable of cutting at the time. I printed out some stencils to trace onto wood, and then cut some holes, and installed the parts from the prototype onto the board. And it looks pretty rough because the 3D printed parts are still there, but I think it looks a whole lot better than it did before. It's a step in the right direction at least. But how did it work? And this is where I gotta be honest with you, it didn't work that great. The mechanism that I built before didn't have near enough precision to account for the longer tone arm length. So previously it was made to operate with a shorter length, so you wouldn't need near as much precision, but with the longer length, you had to be a lot more precise in the horizontal movement. And not only that, but my original plan to add a sensor for each record size totally didn't work because there physically wasn't enough room to mount all the sensors. So now I had two new problems to solve. My answer to the first problem was to increase the gear ratio between the motor and the tone arm, thus making it move slower. I was pretty disappointed I had to slow it down so much compared to how it moved with the smaller tone arm, but I felt like this was the only way to make it work with how I had the sensors arranged. This design with gears went through several iterations until I finally decided to have these gears spilling out the bottom of the movement hub. And I also eventually replaced the gears with rubber O-rings since they allowed for smoother movement. Now going back to those sensors, what I ended up doing was actually pretty similar to what I was doing with one sensor. Previously, when the tone arm would move, it would move to the sensor, and then it would move an extra few steps that were determined based on the calibration potentiometer. In this version, I had the sensor back a little further, and then it would move n number of steps once the tone arm reaches the sensor. Each record size had its own number of steps that it would move, which could be set using the calibration button, combined with the play and pause buttons, which now acted as increment and decrement buttons. Now, this design actually worked pretty well and got the tone arm in the right place probably more than 99% of the time. It just had to move super slowly. So at least now at this point, we're back to where we started. Even if the movement's a little slower, at least it's accurate most of the time. Now, that less than 1% of errors came down to the fact that there's no guarantee that the sensor is starting that step count at the exact same time, or that the tone arm even makes it all the way to the record. Basically, we can tell that the tone arm made it to the sensor, but after that, it kinda just has to trust that it's going to make it the rest of the way. I ran this routine hundreds of times, taking a picture each time to see how accurate it is, and it surprisingly landed on the record every single time, with a very small margin of error. Still, I wanted to see if I could squeeze just a little bit more accuracy out of this mechanism, so I tried out a type of movement some older turntables used, which involves bumping the tone arm into the record and then moving a predefined number of steps to the center. Now I didn't get very far into this idea because it wasn't actually any better, and if I wanted it to be usable, I would have to have the platter be smaller than the record, so if I had different record sizes, I would either have to change out platters every time I want to change record sizes, or I would always have to have one platter that's less than 7 inches long. So not ideal. So there were seemingly no benefits, so I ended up reverting to the previous design. And yeah, that basically was the state of the automatic play routine when I left the project off. There were still more improvements I wanted to make, such as making the tone arm able to move faster and taking care of that less than 1% failure rate. So as we resume this project, I'm looking to take care of all of those problems and make this routine a lot more reliable, and I have a lot of ideas for how I want to do that. And we'll go over that a little bit later in the video. Okay, so remember how I said I only have two new problems to solve? Well, there's actually another one, and it revolves around the pickup sensor. You see, the previous version of the turntable worked by tripping the sensor and immediately initiating the homing routine. So wherever the sensor was, that's where it would pick up the tone arm. And this worked totally fine on 7-inch records because the inner locked groove is always at the same place. But that locked groove on an LP is different, and also different on 10-inch 78s. So if we want to pick a specific point to pick the tone arm up at the end of the record, we would need at least 3 different points in order to get it to be reliable to any degree. Now when a record ends and the stylus is starting to drag into the dead wax, the tone arm moves at a slightly faster rate clockwise because the groove spacing is super wide in the dead wax. And records are cut this way specifically to trip automatic mechanisms, even dating back to the 1920s. So my thought process was, I just need to design a system that can detect this extra movement at the end of the record. Easy, right? I attempted to implement this using the same pickup sensor as before, but instead of interrupting the sensor using a solid interrupter, I made a comb that interrupted the sensor several times as the tone arm moved across the record. In the code, this essentially checks how many times the sensor trips on and off per rotation, and if it exceeded a particular interval, it would know the tone arm is at the end of the record. Because it calculated per rotation using the speed sensor to determine this, the algorithm worked no matter what speed the turntable is spinning. Surprisingly, this worked pretty well. But due to limitations of my FDM 3D printer and the inaccuracy of the sensor I was using, it wouldn't always trigger the homing routine at the right times. Additionally, this sensor alone couldn't determine what direction the tone arm was moving, so it could technically trigger if the tone arm moved back and forth over the rising and falling edges of one of the comb teeth. This would be especially prominent for records where the grooves were pressed off center, of which there are many. But records that did have a large enough dead wax size, it worked every time, very reliably. So with this, I knew I was at least on the right track. I just needed a bit more resolution. In a later revision, I started experimenting with an encoder, and I tried to 3D print a code wheel on the rocker arm, which is similar to the approach I plan to take in the future. But this is when life took over, I got busy, and halted the project. For the future, I'm planning to solve these accuracy problems by continuing what I started at the end of this revision, and trying to use an encoder. I really do think the encoder is the answer for my pickup routine and for my play routine, so I think using an encoder for these scenarios will solve pretty much all of those problems. Now you might not expect this one, but the turntable itself also went through several revisions between the last version that could only play 7-inch records and this one that could play all sizes. And that primarily had to do with one reason, which is the speed. One of the problems that the last version had was the speed would slowly rise over time. So I could start a record at 45 RPM, but by the end of the record it might be at 48 RPM. And I learned in the last revision that this is because I wasn't using a voltage regulator, though I will admit I tried to avoid this as much as possible, but you can't delay the inevitable. I needed a voltage regulator. But before I realized this was my main problem, I tried several other things, such as buying a more expensive motor and increasing the ratio between the motor pulley and the turntable. As you'd expect, neither of those things worked. In fact, increasing the gear ratio only made things worse because now the motor had to spin several times faster, thus creating more rumble at higher speeds. Anyway, once I discovered the magic of adjustable voltage regulators, I decided to try this out, and it seemed to work really well. Well enough that I tried to make a PCB with this approach. This PCB consisted of 4 trimmer potentiometers, one of which would be selected using the pins over here, and these selections would be facilitated by these analog multiplexers, which routed the adjustment lines to the correct places, in theory. Problem was, I never got it to work. I finished this board right before life became busy and never got the time to fully troubleshoot it to get it working. And you know what? This might not be a problem at all because I don't think this is even how I want to solve this problem anyway. You see, my table saw uses a 3-phase VFD, which allows pretty precise control over its speed. All I need to do is change the frequency and the motor speed changes. Now looking at that, I thought there's no reason I can't do that on a smaller scale in a turntable. And it turns out, small 3-phase motors are pretty common to find. I've seen these used in drones and other model aircraft, so I'm wondering if I can use these for the turntable. Furthermore, I could just build my own 3-phase motor into the turntable and have a direct drive mechanism, and this is what my good turntable does, I suspect. At least, that's what it looks like it does. But these are all going to have to remain possibilities for now because, like before, I'm probably going to start with the automatic movements before I move to the turntable in this revision. Now let's take a walk through the PCBs. This is the first version of the PCB. We went into detail about this one in the last episode. All I'm going to say here is that this is the first PCB I ever designed, and it's 99% composed of through-hole components, with the exception of a couple logic gates. Additionally, everything's on one side of the PCB. The other side only contained traces, so not really an efficient use of space. The next version of the PCB saw a lot more surface mount parts. This board is pretty similar to the previous version, except I removed 2 unused potentiometer locations, and a lot of through-hole parts were replaced with surface mount equivalents. I also replaced the turntable's motor transistor with a relay because I thought that might solve some of my speed issues. The next version of the PCB is pretty similar to the last, with the main difference being the elimination of a lot of components around the motor control circuit. This was when I decided to rely on the motor's built-in voltage regulator to attempt to solve my motor speed issues. This revision was the first version that didn't have any bodge wires or need any touch-ups. It's also important to note that at this point in development, the turntable could still only play 7-inch records. So if I decided to finish the turntable in this form, this PCB would have been the one to stay. But during the use of this version, this is when I decided to increase the size of the turntable, which is why you see a lot of things crossed out. I realized that for a full-size turntable, I would have to rethink the design. Now the last version of the PCB that I physically made was the one that would accommodate all of the changes I made to upgrade the size. It's massively different from the previous version and showcases pretty well just how bad the scope creep got. Just quickly going through the new parts, there is now a strobe relay, encoder hookups. I replaced the solenoid circuit with an H-bridge circuit to drive a linear actuator, and that would engage and disengage the motor with the horizontal tone arm movement, because the solenoid's sudden movements would sometimes knock the tone arm off its target. An audio cutoff circuit that would cut off the audio whenever there's a movement running or when the tone arm is homed. 4 hookups for 4 speed potentiometers. These were chosen via 2 bits of the digital logic from the microcontroller, which would select one of the potentiometers in combination with one of these resistors using these 2 relays. So not only did I completely uproot my original design, I added several new features to it. Surprisingly, most of these features worked fine and were actually functional in the second version, after I added some bodge wires to fix some errors, of course. But anyway, the only thing that didn't work well after this was the motor. When the motor was plugged into the board, the voltage dropped so much that it ran way too slowly, and this made sense because there was just too much current being drawn in one place. Now moving on from the PCBs, you got a little sneak peek into some of these features, but some of the features that I included with this new version include a strobe. I eventually wanted this to replace the digital speed display because it's a lot more accurate and it looks way cooler. Unfortunately, this strobe design was super difficult to see, but this could be improved in the future. And this strobe worked using a transformer and a resistor to step down the wall power to something an LED could use. This approach worked really well, though later on I realized I could just use a 555 timer as an oscillator adjusted to match the 60 Hz that my wall AC power provides. And the other feature is a tone arm lock. This looks so goofy, but it was just a prototype, so I didn't really care that much. It did work really well though, so I'm hoping whatever I design in the future works just as well as this one, but doesn't look as silly. So now you've seen all the poor design choices I made, and I'm sure you're probably wondering what this thing looks like while it's working. Well, 3 years ago, I recorded a video showing all of the features that I had implemented at the time, so let's go see what Past Me had to say. Let's turn it on. When you turn it on, you see that the speed is 0. That's the speed the turntable's spinning. But if we spin this, we can see that the reason is there's an optical sensor hidden under here that's detecting how fast it's going. This hole was a strobe. I ripped that out though. That's going to be coming in a future version, and that's going to be replacing the digital display for the speed here. This thing over here, this is the anti-skate. Wait, here's our settings. When we hit this is the pause button. Lifts the tone arm up so we can move it and cue it. And when we press it, it sets it down. This pause button here, when you set the tone arm down over the home position, it goes down quickly. But if you set it down anywhere that's not the home position, it sets it down slowly. That's so it doesn't damage the record when it, comes in contact with it. Right now this supports 3 different record sizes. They're determined by this switch up here. Up at the top is 12-inch, in the middle is 10-inch, and at the bottom is 7-inch. So let's put a 7-inch on first. Actually, let's put a 12-inch on because I don't have the 7-inch adapter right now. Now this center part's broken off, so I kind of gotta center it a little bit there. That's okay. Won't be broken off in the final version, I'm sure. But anyway, we have it set to 12 inches now, so when we click this button, it'll lift up and place the tone arm on the record. The accuracy is a little bit questionable, but it gets there in the end. It's not falling off the record or anything, so that's cool. So when we click this again, it's going to return home. So now I'm sure you're wondering, how does it know where to place the tone arm? You have this sensor over here. You can't see it, but it's there. There, that sensor that I'm pointing to. Now if I lift this up and I move the tone arm, you'll see that sensor light up when it passes a certain point. That sensor is used that when it passes that sensor, then it starts counting steps towards the center of the record. And how many steps it knows to go, that is a value that you determine. When you hold this button here, it shows you how many steps it's going past that sensor. So right now it's going 555 steps. For a 10-inch record, it's going to be a few more steps, 835. And for a 7-inch record, 1230. So that's a value that you set. So like I said before, you could set any size technically, but the standard sizes are 7, 10, and 12-inch. Anyway, to demonstrate how that's working, or demonstrate changing it, let's go back to 12-inch. And this is at 555 right now, so 555, I'll try to remember that. And you use these buttons to increment and decrement this value. So the home button decrements and the pause button increments. So that makes sense with how they're positioned. But you can also hold them, and it'll change that value. So if we put that to 391 and we let this go, you're going to see the blue light flash a little bit. That means the value's changed and it's saved. If I just press this again, then no blue light flashes because it's not saving anything. So now if I run this routine again, it's going to land quite a bit before the record because it's not going near as many steps. But let's return that back home. And let's bring that back up to 555. And when we do that, it's going 555 steps, which is right to the outer edge of a 12-inch record. Now, some of the inaccuracies with this approach come from the fact that, so when it lifts up and it moves to the outer edge of the record, it moves pretty quickly. You might be able to see it, but it kind of bounces back and forth a little bit when it gets to the end. And that's one of the faults that causes it to be a little bit inaccurate, because it's moving too fast. But we also want it to be fast so that you're not waiting forever to get your record played. But that's something that I'll be addressing in a future version. This is kind of a sneak peek of what it's going to look like. But this is an encoder, and this is a code wheel. So we're going to be monitoring the position of the tone arm in the software at all times. So it's always going to know where it's located. And when this encoder is moving, if it stops moving, it's going to know the tone arm has stopped. Or if it starts moving more quickly, it's going to know it's at the end of the dead wax of the record. So that's pretty much how this is working right now and possibly in the future.
not broke, but badly bent. I'm not down to my last cent, 'cause I got $1, but it's my last dollar bill. Yes, sir. In my pockets, there's a dent. All my dough is nearly spent, but I got $1, and it's my last dollar bill. Oh, I'd love just one more buck fortune left me by chance. Now here's a hint, I feel like a mint. You can hardly tell by a glance. I don't care, no millionaire can give me the icy stare, 'cause I got $1, my last dollar bill.
And there you have it. That's pretty much everything that was going on with this turntable up until I stopped working on it in 2023. And in that hiatus between then and now, I've had a lot of time to think about what I could have done differently on this project and what I should have done and ways that I can improve things. And I'll be honest, I think it's just better that I start this project from the ground up. In my past ideas, I was on the right track for a lot of things, but things could have been implemented a lot more cleanly and they could be a lot more robust. And I really want to get that accuracy up to 100%. And a lot of these pain points I encountered probably could have been avoided if I had just stuck with one design from the beginning. So that's one thing that I really want to get right this time. So I pretty much have my mind made up that I'm going to restart this project, so I have a lot of parts to go through and a lot of things to organize, and not to give spoilers, but in the next episode I'm going to go into organizing those parts, and I'm going to get this version, which is Prototype 2, up to a bare minimum working state. I just want it to be able to play records. It's not going to have any automatic functionality or anything, but I just don't want it to go to waste. These are good parts that can be turned into a turntable, so we'll do that. Now, I'm feeling pretty optimistic about these ideas I have for the future version, and I want to see if that optimism's deserved, so join me in this journey and we'll see if that optimism is deserved. Thank you for watching.